Hi all, in this video we introduce the computation of the gradient of the flow map for a two-dimensional steady or unsteady velocity dataset. Again, we start with some general import statements where we need to make sure that we have all the directories include all the necessary directories. That's the same stuff as we have been doing in the last videos. Now, the crucial question is, why do we need to compute the gradient of the flow map and why is it important? So the gradient of the flow map is related to the Cauchy-Green strain tensor. So in order to compute the Cauchy-Green strain tensor, which is the deformation tensor, we actually need the gradient of the flow map. And the Cauchy-Green strain tensor is important because it contains really necessary information when extracting elliptic or hyperbolic Lagrangian coherent structures. Now to the computation, so to the gradient of the flow map. So we assume that we have a trajectory starting at x0 over some finite time interval t0 to t. And we initially perturb this trajectory in the direction of this vector x0. So x0 is simply a material vector and represents the direction of the perturbation. Now this material vector will evolve along this trajectory. So basically, as I move on this trajectory, this material vector will evolve according to the equation of variation. We also call it, we also say that the vector c evolves materially. Now, the solution to this ODE is represented by the gradient of the flow map times the initial vector x0. So in order to see how this vector x0 evolves along a trajectory, we simply need to multiply it with this matrix here, which is the gradient of the flow map. Now, for two-dimensional velocity fields, the gradient of the flow map is a 2 times 2 matrix. So we have a 2 times 2 matrix times a 2 times 1 vector, of course, gives a 2 times 1 vector. Regarding the computation, so again, we will show how to compute it on the Aviso dataset. So again, you can see we just simply import the Aviso dataset. That's again the same stuff as we've been doing also in the previous videos. So the first 3 points are exactly the same, and I will not go through them. The critical point is the computation of the gradient of the flow map. So how do we eventually compute this gradient? How we numerically compute this gradient in a reliable way? So we're interested in computing this gradient at this point here. So we want to compute the gradient of the flow map at this point x0. In order to do that, we seed 4 auxiliary trajectories, which are simply spaced evenly in the x and the y direction. So we place 2 trajectories next to each other in the x. So here one is the green one and one is the blue one, and we place 2 trajectories next to each other in the y direction. So one is the red one and one is the orange one. And then once we have these 4 initial conditions, we simply compute the trajectories initially located at these 4 points. Now, these 4 points, you get 4 trajectories then. And of course, this initial cross, or this initial, we also call this auxiliary grid, which is specified by the values delta y and delta x, will deform accordingly. In order to compute the gradient of flow map, hence we have now 4 trajectories, which initially were separated, which were initially placed on this auxiliary grid. In order to compute the gradient of flow map, we simply evaluate this quantity, which where it is important to say that x1 simply denotes the first component of the trajectory. So basically, we take, let's say, the first green trajectory here, the endpoint, and subtract it from the left one. And then we divide it by the initial spacing. Then, in order to get this quantity, we take the red trajectory at the endpoint, and subtract this point here, and then divide it by 2 times delta y. And we repeat the same step also for the second component. So here I call first and second component. So the first component simply would be the x component of the trajectory, and the second component simply will be a y component of the trajectory. Now, I use the same notation as it is used in the book. In fact, I also strongly encourage you to check out the reference in the book. Now, in order the computation, so how do we compute on the gradient of flow map? So the computation basically follows the same as the one of the flow map. In fact, we first need to import this function, which is called gradient of flow map. We need to specify a time interval with an appropriate time step. And also we need to specify an initial condition where we want to evaluate the gradient of the flow map. As I said before, if we want to evaluate the gradient of flow map simultaneously for several initial conditions, then this vector will simply become a 2 times n vector, where n is simply the number of the initial conditions. In our case, this is simply a 2 times 1 vector because we just have one initial condition. And the first component is simply the x coordinate of the initial condition, and the second one is simply the y. Or you can call it, this one would be x1 and this one would be x2. Now, as we can see here, we needed an auxiliary grid. And of course, the spacing of the auxiliary grid is arbitrary. I mean, it's arbitrary in the sense that we can define this parameter. Now, of course, the finer, so basically the shorter this distance, the more reliable the computation. The further apart, the less exact the gradient will be. Now, of course, if you choose it to be too small, then you might encounter numerical issues in the sense that if you're, let's say, go to floating point accuracy, then you will have problem sets. So there's basically a trade-off, but a sensible value is generally to choose it so one can relate this to the actual spacing of the data. So dx data is simply the spacing between the x grid of the data, and one can relate the auxiliary grid simply to the spacing, and one can specify, okay, I want the auxiliary grid to be 10 to the power of -3, so 0.001 times the original spacing of the data. You can, of course, you can experiment this and make it smaller or bigger and see what kind of differences you have. Now, this gradient of the flow map takes as argument, again, 2 principal arguments. One is the time and one is the initial position. So this is simply the time interval over which you want to compute the gradient of the flow map, and x0 is simply the initial position. The rest of the arguments, they're basically the same as the ones we encountered for computing the flow map. So here we have, again, the grid of the data, the interpolant, where it's periodic or non-periodic, the domain over which the flow field is defined, whether it is steady or unsteady, and the time array of the data. And then last but not least, we also need to specify this auxiliary grid, because that's an additional basically variable we need to specify when computing the gradient of the flow map. This was not necessary. This was not necessary when computing simply the flow map, simply because you were not. So we were just considering one trajectory and there were no gradients to compute. Now the output, we can calculate this, and the output, if we take a look at the shape. Oh, of course, I need to run actually all the scripts. So I forgot to run the initial script. So I actually need to run all the scripts. I need to make sure to import the data. I just need to run all the scripts. Otherwise it will not compute, of course. And this gradient of the flow map returns an array. The array has dimension 1001, y1001. So the first dimension simply takes care of the time. So at every point in time, at every point in this time array, we will have a gradient of the flow map. Now, of course, if we choose the initial time to be 0, then the gradient of the flow map should be 1. Let's check this. So then the gradient of the flow map simply should be unitary matrix. So sorry, not unitary, the identity matrix. So if we are just like interested in the first component, you see we get as an output, we simply get the unit matrix. Identity matrix. Now, why do we have this 1 here? Because we're just considering one trajectory. So of course, you could also consider multiple trajectories and do this computation in parallel. That's completely fine. Then you would have here not 1, but the value greater than 1, depending on the number of trajectories you have. So if you do 100 trajectories, then you will have 100 here. This 2 is simply the matrix. So if you want to access, let's say, if we want to access this component of the matrix, so the first one, we simply need to type, okay, let's say, and now I want to access the gradient of flow map at the last point, so evaluate over the complete time interval. And let's say I want to have the upper left component, which is 1.23 in this case. If we want to have the complete matrix, then we just like can run this command, and this will return us the complete matrix. So that's basically the gradient of the flow map over the time interval 0 to 10 for a trajectory launched from this initial condition. Generally, one is not interested. So even though this function returns the gradient of the flow over the full time interval, one is just generally interested in the last component. So if you just want to extract the last component of this array, then you simply need to run this command.